Ever wondered how classical and quantum computers work? Let's delve into the heart of these technological marvels. Classical computers, the bedrock of the digital age, use bits to represent information, much like a light switch. 0 for off, 1 for on. These bits, governed by classical physics, carry out computations in a predictable, deterministic fashion. From the monolithic mainframes of yesteryears to the sleek laptops of today, classical computers have been instrumental in shaping our digital world. Now, let's step into the quantum realm. Here, quantum computers come into play, employing a different kind of bit, the qubit. Unlike classical bits that can be either 0 or 1, qubits can exist in multiple states at once, thanks to a principle called superposition. Think of superposition like a spinning coin. While in the air, it's not just heads or tails, but a blend of both. It's only when we catch it that the coin lands on one side. This ability to be in multiple states simultaneously allows quantum computers to process vast amounts of information in parallel. It's like being at a crossroads, and instead of choosing one path to follow, you explore all paths at the same time. This simultaneous exploration potentially gives quantum computers a speed advantage for certain types of problems. But the quantum world doesn't stop at superposition. It brings us to another intriguing concept: entanglement. To understand entanglement, picture a pair of magical dice. When you roll one dice, no matter how far away the other is, it instantly knows what the first dice rolled and mirrors the result. It's as if the dice are mysteriously communicating with each other, creating a unique interconnectedness. This entanglement allows quantum computers to link qubits together in a way that whatever happens to one qubit can instantly affect another, no matter the distance. This interconnectedness provides an added layer of complexity and power to quantum computing, enabling it to solve problems that are currently beyond the reach of classical computers. So, in the quantum world, superposition and entanglement work together, creating a system that can process multiple possibilities simultaneously and link information in ways that classical computers can't. It's as if the dice communicate mysteriously, providing a unique interconnectedness. Despite their potential, quantum computers face challenges. Like a virtuoso violinist, quantum computers require precise conditions to perform their magic. The qubits, the basic units of quantum information, are delicate creatures. They demand an environment of extreme cold, colder than the depths of outer space, to maintain their quantum state. This state, called coherence, is akin to a perfectly tuned violin string, ready to vibrate and produce a note at the bow's slightest touch. This requirement presents a significant challenge. Maintaining such low temperatures is an intricate, expensive endeavor. It's like trying to maintain a perfect silence in a bustling city, a task that requires significant resources and constant effort. Just as the slightest noise can disrupt the silence, even minute environmental changes can disturb the delicate quantum state, making quantum computers susceptible to errors. Yet the potential of quantum computers is immense. They promise to tackle problems that are currently out of reach for classical computers. Let's consider the field of cryptography as an example. Picture cryptography as a locked box. A classical computer attempts to unlock the box by trying out different keys one by one. Depending on the complexity of the lock, this process could take an extremely long time, even with the fastest classical computers. On the other hand, a quantum computer, thanks to superposition, can try multiple keys simultaneously. It's like having a master locksmith who can handle many locks at once, significantly speeding up the process. This potential advantage makes quantum computers an exciting prospect for fields such as cryptography, optimization, and drug discovery. It's important to note that quantum computers aren't here to replace classical ones, but to complement them, just as in a symphony, where each instrument contributes to the beauty of the whole. Classical and quantum computers harmonize their strengths to solve complex problems. The robust and reliable classical computers, like the steady rhythm of drums, provide the foundational beat of our digital landscape. They're excellent for tasks that require deterministic sequential computation, akin to playing a well-defined note sequence in a melody. Quantum computers, on the other hand, are like the violins in our symphony. capable of producing a range of tones simultaneously. They're designed to tackle specific problems that classical computers struggle with, such as factoring large numbers or simulating quantum physics. It's like playing a complex harmony, exploring a range of possibilities at once. In this grand symphony of technology, each type of computer plays its part. Classical computers provide the steady rhythm, while quantum ones add the rich harmonies. Each plays a unique role in solving complex problems. In conclusion, classical computers laid the groundwork, while quantum computers open new avenues. We've journeyed from the binary world of classical computing, where information is like a light switch, to the quantum realm, where that switch can be both on and off at the same time. We've ventured into the intriguing concept of superposition, which allows quantum computers to explore multiple paths simultaneously, like a spinning coin in mid-air. We've also touched upon entanglement, a phenomenon that links qubits in a unique bond, akin to a pair of magical dice. And we've acknowledged the challenges quantum computers face, like delicate instruments needing perfect conditions to perform their magic. Remember, quantum computers aren't here to replace classical ones, they're here to harmonize, each playing a unique role in our digital symphony. As we continue to navigate the evolving technological landscape, understanding these concepts is more important than ever. Thank you for joining us, and stay tuned for more explorations into the world of computing.